Hello, everyone. Welcome back for some more calculus. Um, Today we're on section 5.3, first derivative test, second derivative test. It's just more of an application of how to use derivatives to figure out what's going on in the graphs. The beginning of this is going to feel exactly like yesterday because I kind of preloaded yesterday's because it's hard not to talk about minimums and maximums when you're talking about increasing and decreasing. So we're just going to add that on. It's going to be nothing new at the beginning and then one new thing at the end. So we have this thing called the first derivative test. The first derivative test basically tells us when something's a minimum or maximum. It's exactly what I did yesterday on that number line. So what I'm about to do right now is a complete repeat of yesterday. It's just actually now formalized to call a test. So you may remember yesterday I took a derivative. I think if I remember right, I had a negative 2 over root 3 and a 2 over root 3. This was my critical points. And then I did positive, negative, positive. And I knew that this had to be a maximum because it went from increasing to decreasing. And then this had to be a minimum because it went from decreasing to increasing. So that's all the first derivative test says. So notice if the first derivative changes from positive to negative, there's got to be a local maximum. Second part of that theorem says if that first derivative changes from negative to positive, then there's got to be a local minimum. It's just because up, down, or down, up. Sometimes you can get critical points that sign does not change. So if that happens, if you get a critical point but the sign doesn't change from positive to positive, negative, negative, positive, then there's just no local extreme there. It's not a minimum or maximum. So we did one of these examples yesterday. Let me do one that looks a little different. Today we'll do this one. The other one there is just another polynomial. So I'm going to slide down to the bottom here. And let's see here. We're going to go f of x equals, we'll just go through that same exact process that I just did. Okay, so remember, first thing, take the derivative. It's a product rule. So it's sort of the first term, which is 2x times the second, which is e to the x, minus the derivative of the second, which is e to the x, times the first. All right. Now we want to set that equal to 0. Usually we just leave it like that and factor because when you do these product rules, they always tend to look the same. So we're just going to factor. So notice there's just an e to the x in each term. That's it. Sometimes there's more, but there's just an e to the x. I'm left with a 2x minus, be careful with this minus on here, x squared minus 3. I'm going to do some simplifying in there. I get e to the x, I get negative x squared plus 3 plus 2x, and I'm going to take that negative out because the factoring of that can be a little tricky. So I'm going to take that negative out and just bring it out here, negative e to the x, and then I'm going to be left with x squared plus 2x plus 3, and I go one step, I do my factoring, I get x plus 2 and x plus 1. So I get critical points whenever the derivative is equal to 0 or it's undefined, right? Sorry, I lost that 0. But it's never undefined, and it's only equal to 0 at negative 1 and negative 2. So now I do that little number line again, negative 2, negative 1, and then I go plug in. So all I got to do, pick any point. So I'm just going to pick a point out here, and I'm going to plug it right into here. It's always easiest to plug it into that factored thing because it's really easy to find positive versus negative. And remember, all I care about is positive versus negative. Notice e to the x is always a positive number, so that number out there is always negative. So I can just kind of leave it out there, but I got to remember it's there. It's always negative. And then if you put a big negative into this term, the x plus 2 term, it's negative, and into the x plus 1, it's negative. So you got negative times negative times negative. So that's a negative number. I'll do the really easy one. The easy one's to the right. So we go way over to the right, like a big positive number, positive x plus 2, positive x plus 1, but negative there. So that's the negative. And then in the middle there, this gets a little trickier, like negative 1.5. This number here inside there is going to be positive because negative 1.5 plus 2 is positive. Negative 1.5 plus 1 is going to be negative. I don't care what the number is because I'm just need to know whether it's positive or negative. So I got positive times the negative, but then I got the negative out front. So that's a positive. Therefore, local minimum, because it's going from negative to positive, and local max. Now, they might ask me for global mins and global maxes. If they do that, then I need to draw a picture, maybe plot some points, see which one's highest, right? Because one might be higher, one might be lower, that sort of thing. Okay. It is possible that you do this number line thing, just so you know, and something like this happens. Okay. That just means that there's no critical point 3. It does mean, though, however, remember, if it was equal to 0, it's a critical point. So it was probably like a horizontal tangent or something. Here's a really quick, simple one. Watch this. Y equals x cubed. Derivative is 3x squared. You set that equals 0, you get x equals 0. So we have a critical point at 0. However, when you plug it in, squaring it, it's positive, positive. You all know the cubic graph looks like this, right? So it's actually not a minimum or maximum, it's actually a horizontal tangent there. It is going to come up in the next section, not the next section, the next question, actually, because that does have a name. Something else is going on there. Okay? So that's, I think, all there was there on, that's really the same thing as yesterday. So now we got some additional stuff. It's called concavity. So the concavity of a graph, this is called concave up. Anything that's kind of like an upwards parabola is concave up. And this is called concave down. So now we're going to talk about how to figure out when a graph is concave up and concave down, and it has to do with the second derivative. So before I get to that, let me draw you a little picture here. I don't want this to take too long, so I don't want to kill you with all this proof, but I just want to talk a little bit about, so concave down, you can see that this graph is concave down. I'm just going to cover it in orange, kind of from here to here. Okay, kind of from here. And then it changes to concave up the rest of the way, right? Concave up. So what determines that concavity is actually the slopes. And notice I'm going to draw on some slopes. Now it's not positive or negative slopes anymore, because notice positive slope, positive slope, positive slope, positive slope, but now negative slope, right? So there are some positive and some negative. However, if you notice, all of these derivatives are getting smaller. Big positive, smaller positive, smaller positive, 0, then negative and steeper negative, so they're getting smaller. And then if you look at the other side over here, they're actually getting bigger. Smaller, 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 smaller. Here, they're increasing, okay? Negative, smaller negative, even smaller negative is 0, so they're increasing. So now if I go back to that, then what that's going to tell us is this, okay? If the first derivative is increasing, that graph was concave up. Let me come back here again. I'll go back there. Don't worry. Notice that concave up, first derivative is increasing, right? But also remember that if that first derivative is increasing, okay, sorry, yeah. So if the function is concave up, if the first derivative is increasing, okay, it also means that that second derivative, if the first derivative is increasing, just like if a function is increasing, that means its derivative is positive, right? That was the last section, last problem. So then we go one step further. If a function is concave up, that means its derivative is increasing, but if the derivative is increasing, the second derivative must be positive. It's the same relationship between the first derivative and the second derivative. And concave down, the second derivative must be negative. So really what you're looking for here, this was all kind of helping you. Concave up if the second derivative is positive. Concave down if the second derivative is negative. Okay, that's all there is to it. All right. So let's see. A point, I'll do an example problem here in just a second. A point where the concavity changes, remember this one right here. Oops, sorry. This one, oh gosh, I erased it. Sorry. That point right there, the concavity change, that's called an inflection point. Concavity changes here, it's called an inflection point. All right. So that's the definition of an inflection point. I will do an example here in just a second. I want to just throw in the last terminology. There is a second derivative test. The second derivative test is also a way to tell us if there's a minimum or maximum. If the second derivative is positive, that means it's concave up, right? And if it's concave up, there's got to be a minimum point. So first derivative is equal to 0, tells me it's either a minimum or maximum. If I just go look at the second derivative and it's positive, then it's a local minimum. If it's negative, then there's a maximum. Normally you wouldn't do the second derivative test because the first derivative test can tell us whether there's something in the minimum or maximum. So most of the time, the second derivative test isn't totally useful, but sometimes it is, and we'll give you some examples of when it is. So let's, I don't know, what's my best example here? We'll do one quick example, I'll be done. Let's just do this one right here. They're all kind of the same. X cubed minus 12x minus 5. I'll walk you through everything. And then you can look at other examples. There are always more examples in the book. I just don't like to do too much here. If you don't need to see them, that's fine. So here we go. Derivative 3x squared minus 12. If I needed to find first derivative stuff, I could do all the same stuff I've done before. I'm going to skip that right now, actually, just to save some time for you in the video. But they might ask increase. Now you can ask increasing, decreasing, concave up, concave down, local min, local max, global min, global max, inflection points. You can ask any of these combinations of things. Sometimes we'll just skip the first derivative if we're worried about the second derivative. Sometimes we'll ask them all. So I'm going to skip the derivative right now. We're just going to do the second derivative, which means I'm going to answer concave up, concave down, and inflection points. Okay. So second derivative is very simple, right? Just 6x. This is not a great example, I guess, a little too easy. Now we set that equal to 0. We're going to do the same thing we did in the first derivative, so you get x equals 0. That means this is a possible inflection point. It may be an inflection point. It might not be an inflection point. We have to check it. So now I'm going to plug in the same way. I'm going to plug numbers in, but I'm going to plug them into the second derivative, not the first derivative, because the second derivative is going to tell me concavity. So I plug in a negative number. I get out a negative. I plug in a positive. So that means it's concave down from negative infinity to 0. Notice the interval notation. Concave up from 0 to infinity. And there's an inflection point at 0, and I can plug it in. It's actually -5 when I plug it in. So that was a pretty easy example. There are other examples you can look at the book. We're going to do plenty more. I'm just going to let you try them on your own, and we'll go from there. So have a nice try with this homework, and we'll talk to you tomorrow in class.